Guys, so at some point you wake up as a data scientist and wonder what are we doing? And there's lots of different schools out there nowadays. And you sometimes then get to the conclusion that if you're doing things with data, there tend to be these three schools of doing things. There's these people that people call frequentists, there's these people that people call Bayesians, and there's these people that call themselves machine learning specialists. If you've gone to a Dutch college, then you'll probably be taught that. If you did something in computer science, you've probably done that. And I always found that this Bayesian thing is something we don't really do too much in Europe, and all the cool things I see online always happen in the US. So I figured it might be fun to do a small talk on that, because thinking like a Bayesian does feel like you can always apply some duct tape to whatever you're doing with data. It is going to be a little bit math heavy, so I'm going to give you guys a couple of textbook examples, introduce the idea of Bayes. I'm going to show you some moments when doing some Bayesian statistics really shines. I'm going to introduce how to do probabilistic graphical modeling in Python as well. I'll even give an explanation of how you can use Bayesian statistics to do OR algorithms. And then at the end, I'm going to show you guys a good algorithm to predict Heroes of the Storm match outcomes. I hope we're all excited about that. So textbook Bayes rule. Probability theory is kind of nice, because if you think about it, Laplace summed it up quite nicely. The theory of probabilities is basically just common sense reduced to calculus. If you want to talk about the likelihood of something happening, probability theory really helps you quantify it in the most exact way that there is, which also means that if you just make a couple of assumptions, you can leave the rest of probability theory and you will have your model. So this is what Bayes' rule looks like. This is sort of probability 101, I guess. But the best way to explain it, so there are two events, and suppose I know something of one event, let's call that event B, then I might have a different belief on what event A might be. And if I want to know something about A, and I know B, then I can use Bayes' rule to do some inference. Simple example, suppose that I have a couple of dice. If I have one die, then my belief of how many eyes I get to see is different than if I have two dice. So one way of looking at it, my belief over the sum of the eyes that I see depends on the number of dice that I'm rolling. In this case, this would be the probability of eyes given the number of dice. You can also look at it the other way. Suppose I want to know the probability of the number of dice that I've cast given the number of eyes, then instead of looking at it from this direction, you would simply look at it from this direction. That's sort of the nice thing about inference. If I know PE given D, then I can infer what PD given E might be. That's sort of the cool trick. And I guess a better example of that would be a textbook example. So suppose that there's an epidemic, and a person has a probability to have a certain disease, and then the authorities decide to test the population, but the test is not entirely reliable. So the test generally gives 1 out of 110 people a positive result, but if you took the test and it has a positive result, there's a very likely situation that you might actually have the disease. So then, as a proper college student, and you're doing something with a textbook, you would just fill in this formula, and a number would pop out. And there's again some inference. So if I didn't know what the result of the test was, this would have been the probability that you actually had the disease. But given that I now know that you took this test, I can apply the probability statistics that I know and come to a probability. But we kind of know a bit more. So if this is a situation and I know only these three probabilities, I might actually be able to figure out some other useful metrics. I will try to keep the math light, but hopefully this isn't such a weird thing to assume from you guys. If I know the probability of t, so that's a probability that the test came out positive, then I can split that up into two situations, namely the test came out positive and you had the disease, and the test came out positive but you didn't have the disease. And then I can sort of apply a version of Bayes' rule again to say, oh, but the probability of that you have the disease and that the test came out positive, that can be written like so, and again. And then I can fill the numbers in again, and suddenly, even though I just calculated the probability that you have the disease when you took the test, I now also know the probability that the test comes out positive if you don't have the disease. What else can we know? Well, do a bunch of math. What you can then also infer is the probability that two tests come out positive. Note that in order for that to do, I need the probability that the test comes out positive even though if I don't have the disease. This is a lot of math, so we don't like looking at this. Let's look at it from a more simple way. How about we just turn it into a graph instead? So in a simple situation, if you have the disease, the test result is basically influence. Now, I can take another test, And this is the same representation, the graphical version of it. And the cool thing is, the result of this test is only influenced by whether or not you have the disease. So given if I'm having the disease or not, that's the only thing that influenced the test. So then I can calculate, hey, what's the probability that I have the disease given these two tests? And I'm still just applying probability theory, but even though in the beginning I only really knew stuff about this, I can infer this. And if I do another test, I can infer that as well. And that's kind of so this is sort of the cool thing about probability theory. You know that these values are correct because it's just common sense, because it's the laws of probability that we're hearing here. So even though if I only know about you did this one test and then say something about whether or not you have the disease, I can infer what it means if you maybe do two tests. And because it's probability, so this is sort of a probabilistic system, if you will, I can even go one step further and say, well, suppose that I don't know whether or not you have the disease, and I know that you took test 1 and test 3. What do I then know about the outcome of test 2? That is also a situation where you don't beforehand know anything about your training data, but you can infer the rest. So this aspect of we only put a little bit of knowledge in and the rest is done through probabilistic inference, that's a powerful thing. Because via Bayes' rule, we can basically infer information about the probability of you having the disease that you took more tests, even though we initially only knew about the probability of you getting a positive test result given that you had the disease. And the trick here is that we clearly define our uncertainty that we have, and we can infer the rest via probability theory. In this case, the main cheat was that realizing that the tests are independent of one another. Given that I have the disease, the tests are all independent, which means that I can think according to this structure. And notice, that's also kind of interesting, suppose that this is an online system and I'm predicting whether or not you have the disease, then I suddenly have a robust model that, given different forms of input, it is the same system that's performing the prediction. So at prediction time, I can have different amounts of data known to me and still be able to make a good prediction come out. In my experience, most random forest packages in neural networks don't have this property, that if there is a value missing, say there's a null somewhere, scikit-learn will give you an error. So that's interesting. What else could we do with this idea? Well, I like this graphical representation, because it basically allows me to put some domain knowledge in a system and then lets me infer the rest. So people will again give that a name. They call them probabilistic graphical models. So let's think of a probabilistic graphical model, and this will be a silly example, but it's to drive the point across. So let's say I have some domain knowledge, and I'm going to think about a good graph-like structure that describes the situation at hand. So let's create one with this library called pomegranate. It's a library I found that's fairly new, but it does exactly what I want it to do. So let's assume that we want to know if today's weather is predicted correctly. And let's say that there are 3 broadcasters. We've got Alice, she's super accurate. We've got Bob, he's downright terrible. And then we have Claire, and she's all right. So if I know who's doing the prediction, then I can infer something about what the weather's going to be, if the weather's going to be predicted correctly today. This is not necessarily something that happens in real life, but it serves as a purpose as an example here. But suppose I know more. Suppose that I also know that Alice is more of a weekday kind of person, and Bob is a little bit more of a weekend type of person, and Claire kind of does both. That's maybe because Claire is some form of intern, and she's the backup of the two. And you'll notice that given it's a weekday, then a 70% chance that it's Alice, 10% that it's Bob, and 20% that it's Claire. So these probabilities sum up to 100. So given what day of the week, I know something about who's going to be predicting. Given who's predicting, I know something about whether or not it's going to be correct. Let's say, and this is actually not that unlikely, let's say that it is, if it's a weekend, it's actually sunny. This happens a lot in real life because if it's weekends, there's less car about. Less cars means less pollution means less clouds, let's say. Something like that. I'm not arguing that this is the real world, but I am arguing, suppose we had this situation, and I could model it like this. And you can already imagine how useful this might be. Because I can ask all sorts of questions to this system. Suppose the only thing that I know is that Claire is doing the prediction today, then I know something about this situation. But also, because I know that if Claire is doing the predicting today, it's probably going to be a weekday, then I also know that it's kind of likely that it's not going to be sunny today. So you can see that from this system, if I have only one input, it can deal with it. If I have 2 inputs, it can equally deal with it. And that's a nice property. Another thing to notice is that if I know P in this example, so I know the person who's doing the predicting, then knowing something about the day of the week will not have any more influence on whether or not it was correct. This is between D and C. Henceforth, if I know this, D will not be having any influence on C anymore. Also, this is a property that I like. And this is also a thing that is very hard to model with a random forest or a neural network, if you will. So what would the code of this look like? Well, you need the probabilities beforehand. But basically, if you want to use pomegranate, what you would do is you would say, hey, import pomegranate as PQ for some sort of spelling error on my side. And you would then say, well, the probability of a weekend is, 2 out of 7, let's say. Probability for a weekday is 5 out of 7. I'm assuming that the weather channel is always on. And then I can define this conditional probability table, where I basically say, hey, given that it's a weekday, the probability of it being Alice is such and such, and that's how we define it. Once you've done that, you can create a graph where you say, hey, I've defined all these variables. So I can say I have a state for day of the week, I have a state for who, and a state for sunny. And then you make this graph appear. So we have a network. We say, hey, weather, day of the week, that's the thing we want to predict. These are the states. These are the states I've defined earlier. I make a list, put all the states in there, and then I put all these transitions in. And you'll notice at the top of the chain, we have the day of the week, which is linked to S2, which is the who. Day of the week says something about who. Day of the week says something about sunny. And who says something about correct. And then you tell the network to go bake itself. And once the network is baked, you can ask it questions. So you can say, do all of your inference, and let's say that the person who's doing the predicting is Alice. Well, then I'm pretty sure that the person who's predicting is indeed Alice. That's a probability of 1. But what the network will then do is it will do all the inference for you to then say something about whether or not it's going to be sunny, whether or not it's going to be correct, and whether or not you're doing something in the weekday or in the weekend. You'll notice that this is the probability that I put in myself. Given that Alice is the person who's doing the predicting, this is what will come out. That's the arrow we've defined specifically. The other two values are inferred. Similar to what I did with the example with the diseases, doing more tests and doing inference with math, this library is able to do that for you. And again, I put only one thing in. Suppose I put Bob in. Well, Bob was downright terrible, so not only is the prediction kind of worse, but it's also less sunny. One thing we do kind of like is that immediately it does become much more likely that it's a weekend. So that's a nice property. We can put two stuff in. So we can say, yeah, it's a weekend and Bob is doing the predicting. Well, and suddenly, these values are sort of the values I put in. But again, this is an example. I'm putting two things in, and the system can then infer information about the other two things. Nice property. Me gusta. I like this. And let's say that the weather was predicted correctly. So this is a thing that surprises a lot of people. Because if you look at this, you almost get implied that I have to put this in and then this can come out. But as I explained before, if I know the weather was predicted correctly, then it says something about who did the predicting, which in turn says something about what day of the week it might be, which in turn says something about whether or not it's going to be sunny. So if I plug in, hey, today was a correct day, well, it's probably Alice. Alice is great. And it's probably sunny because Alice says something about day of the week, which says something about, etc. So take that, random forests. These are cool properties. The main downside of doing this, of course, is that I, as a business professional, have to come with the idea that this is a sensible way to model things. However, what I get back for it is a very, very flexible model that can deal with missing data at prediction time. It could even deal with missing data at learning time, by the way. Suppose that for some rows of my data set, when I'm trying to learn this, when I'm trying to learn these probabilities, that is, the probabilities that I would plug into this conditional table, if I have a couple of rows that says something about the relationship between D and S, but in the same row I have nothing about this, then I can still make this relationship statistically stronger. It gives me more certainty of the relationship between D and S, even though I don't know anything about the relationship between P, D, and C at learning time. I will need some rows, of course, that connect everything. But if say this bit is very strong and that bit is very strong and this bit is very weak, I can still do inference. So not only at prediction time, but also at learning time, I have a systematic way of dealing with missing data, and I'm adhering to all the rules of probability, which have tons and tons of benefits. So these types of models are very powerful and flexible. One of its most powerful features is that it can handle missing data at prediction time. The example that I've given only handles discrete models. Also, the pomegranate library in general only deals with discrete probability values at the moment. But mathematically, you can also use continuous distributions. There's no real reason why that should not work. Coding these things are a bit harder. So pomegranate is great, but if you want to do something with both discretes and continuous, it becomes a little bit harder, and then you might want to think about sampling. Because technically what you could also do is you could just say, hey, if this is the pattern that I want, how about I just create a giant pandas data frame, millions of rows, and first I generate this column D, and we knew something about how often it's going to be a weekend and how often it's going to be a day of the week. And then I'm going to create a new column called P, which has a sort of if statement. If D has this value, then P is generated according to this process. And you repeat, and then you got this data frame that you can basically ask the same questions to. It's just a group by and a filter and then a summarization at the end. So this feels kind of, I wouldn't call this super Bayesian, but the probabilistic thinking here has helped. So let's look at an example where Bayesian thinking really shines. So in Holland, we have these walls in our garden. And basically what can happen is you can sit in your garden and only very tall people stick above the wall. So if I'm sitting and I'm collecting data, as I am as a data scientist, always collecting, you know so, then I know that what I'm measuring is in principle biased data. So given that I'm measuring biased data, I know how it's biased because I know the height of my own wall. What can I then do to do inference on the actual average height of everyone, if I know that I only measure people above a certain height? And I will leave you to think about that for about 10 seconds, and you may realize that this is a tricky problem. So I know that I have a biased data set, I don't know anything about the total population, and I have to infer something about the total population given some biased data set. And the example that I then come up with is, let's say I have a call center, and I'm interested in knowing how long people wait in line for this call center, and suppose we only measure people that have been waiting for a very long time, because that's when they start to complain. And let's assume that everyone who has been waiting for longer than, say, m minutes, they all start to complain, and everyone below doesn't complain. It's a bit also not the most realistic example, but it's meant to drive the point home. Also, I know nothing about the total population. This is the only thing that I actually know. Because we're going to model a waiting time, it seems sensible that we'll do it with an exponential distribution to look at the intermediate waiting time between people. And let's say I'm interested in figuring out what lambda is. Now, if I know lambda, then I know something about how long it's going to be taking for you to get handled. However, I'm interested in finding lambda. To show how the function works. So basically, a higher value of lambda means that you have a distribution with a thicker tail. So higher lambda, longer waiting times. Okay, Bayes comes to the rescue then. So then, basically, I'm writing down what I want to know. Given my biased data set, I want to know the best value for lambda. Bayes rule. This is the probability that the biased data set comes from this value of lambda. This is what I know beforehand about this value of lambda. And this is the process of how the data gets generated. But if I think about it, I don't really care about this one, because in the end, I'm interested in finding the largest lambda, which means that if it's proportional, I can also just focus on this, which would be fine. And yeah, the entire data set, because this is a likelihood, from a proper distribution of probability, I can basically say, well, the likelihood of getting the entire data set given lambda is just multiplying the likelihood that I have gotten 1 point from that data set and just multiply all the points together. Suddenly, it becomes kind of obvious how to do this. Bayes' rule inspired me towards a solution here. So again, given a certain lambda, I know the probability of the likelihood, I should say, of xi given lambda, given by a function like this. And the only thing I have to now compensate for is that I only measure people here. So the trick you would then do is you would say, okay, this has to be a proper distribution, henceforth I need to normalize something, and I can ignore everything here. So all the x's always fall in here. So then what you do is you normalize it, which is basically an integral where you say, hey, take the density distribution from m, I have this normalizing constant, chug it in, and that way this will be a proper distribution again. And to sort of show how you would do that in Python, you make these two functions, I'll not go too much in depth on how they work because I have pretty pictures, that's always better. So given a certain m, these are the distributions that you would have for different lambdas. And if you would then have different m's with the same lambda, it would look like this. And the functions that I've just shown you real quick, which I didn't explain, generate this. And so again, given a certain lambda, and if I have a point, say, at x equals 10, this would be the likelihood I would have. And I can do the same for all the things in my data set. Now, here I combine it all. Again, the main thing to remember is I'm multiplying things here. And what you then see is, boom, given a certain data set, so suppose I have m is equal to 4 and I have 7, 6, and 8, then this is the posterior likelihood of what lambda might be. So this looks cool, but to convince you, how about I just show you a demonstration where I know lambda beforehand. So let's just generate our data ourselves. So let's say that m is equal to 6, the true lambda is equal to 1. I'm generating some data, and what I'll then do is I'm going to filter some data out if it's lower than m. I'm going to do this a bunch of times and see what happens if I have more data in my data set. So let's say that I only have 6,09 and 6,38, and again, m is equal to 6 here. So I only have 2 data points. And this is what I then know, what I think about lambda, given these 2 data points. This is everything I know. And the true value is equal to 1. So after 2 data points, I'm not entirely in the 1 region, so I could be doing better. Usually the best way to go about this is just get more data. And we get now 6 data points, and already we see it's venturing towards its true value very quickly. That's kind of nice. And I'm also not excluding yet that it might be 2. I'm not entirely certain about my lambda, but my belief is updated. So let's now say m is equal to 2 and lambda is equal to 1, and I'm doing this so I'll have more data points in my sample. And now suddenly, it really is going to start getting close to 1. So as I get more data, I'm able to update my belief accordingly. And the way that I got here is just by applying probability theory and by being reminded by Bayes' rule, which basically then stated, well, if you want to do this, you just follow through. So thinking the Bayesian way really helped in this problem. And with my normal way of textbook statistics, this might have been hard. Another example. So crazy science direction. You could go ahead and do a master's in operations research. It's a very interesting topic. And let's pick a very silly optimization task. Suppose that I have a 1x1 square, and in this 1x1 square, I'm going to create a triangle. And it's of my interest that I'm creating a triangle as big as possible. Now, because we're all intelligent humans, we know that the best triangle should be 1 point in one corner, the other point in the other, and something on the other side, and that's the biggest triangle we can get. But the algorithm would have to figure this out by itself. So how about we just try out a bunch of stuff? There's this function called shoelace, which is on the IPython notebook, but I didn't care about defining it here. Basically what it does is given 6 points, namely x1, x2, x3, y1, y2, y3 to define all the coordinates, then I can calculate what the area would look like. So this is the distribution of the area given random points. I'm drawing random points in the 1x1 square, and this is what the area would look like. So this is the highest value possible, which we never sample, but we sample a lot of small triangles. That's the idea. So this sort of generating process, something with stochasticity, this is what it looks like. So I know something about the probability distribution of A being the area, and x being the coordinates of the triangles that I measure. Let's now try to turn that on top of his head. So let's say I'm sampling lots of these data points, and I can at some point say, how about after I've sampled lots of data points, I just take the points where the area is above a certain threshold. Then I should get a different probability density distribution, something that generates x. And we can pick m in such a way that we do this updatingly. So how about we pick m to be like the half, like the median value. So all the points, so all the areas that are higher than the median, those are the points of interest. And I want to know what the distribution looks like. So now scikit-learn becomes interesting again, because scikit-learn has a kernel density estimator. So what you can do is you can generate all these points and then try to fit a density on top of it, and then try to infer what it would look like if I were to sample triangles that were large. And again, this is still a random process, but just by sampling a bit and using a bit of Bayesian inspiration, I'm suddenly learning that this is x1, this is x2, and x3. So the coordinate for the first coordinate will be combined by combining y1 and x1. And suddenly, all the y's together, it does seem like if I want to have big areas, it would be a good idea to keep y1 and y2 far away from each other. That's something that I'm learning from sampling. The same thing holds for x, by the way. Let's maybe just zoom in on that. So this is the x values, but for the y values you get something similar. So it makes sense if we want to have a big triangle to sample points far away from one another. That's also something you see from the one-dimensional histogram. Now these are actually more interesting. This is where the x's and the y's combine, and then suddenly you kind of realize, well, you know, the difference between the x and the y kind of works a little bit differently. If a y value is low, then the x value can actually be quite big. That's fine. Or they can be close to one another. You can look at this all for a long while, but the main conclusion is I now have a new density distribution that I can sample from. So these are larger triangles, and I have a density distribution to sample from. So where before I was sampling this completely randomly, by then saying, hey, I want to sample from larger triangles, I'm suddenly sampling from this. All of my triangles that I've sampled are larger. And you know, I can, again, cut and repeat. Cut and repeat. And suddenly, through Bayes' rule, I've come to some genetic algorithm. Genetic algorithms work in a very similar fashion. Also, random search, also put a little bit of bias in. The difference being here, I'm doing it rather more probabilistically. So even in the science of operations research, I'm able to be better at the thing that I do by once in a while reminding myself that Bayes' rule is a thing. And a couple of next steps. If you're interested in doing something like this, this works for all sorts of search spaces, and it's actually kind of nice that you can infer statistic properties from the estimations that you get, sort of from the solutions that you get to your OR problem. So we can repeat the same idea until some form of convergence occurs. So note that M can be chosen automatically. So for example, pick M to be the average area that you found from your original sample. But the cool bonus again is that we can use inference on our simulated data to learn more about the nature of our optimization problem. And you should notice something very similar happening with genetic algorithms in general as well. So, so often when I give these talks, like last year I did a talk on World of Warcraft, I noticed that half the crowd came because they wanted to know more about World of Warcraft, and the other half of the crowd were interested in data analysis. Does anyone know this game? So this is Heroes of the Storm. This is sort of the new benchmark Uber game from Blizzard. And the way that it works, you have all these games like World of Warcraft, and they have sort of these hero characters in their story. And in this game, they take all the characters from all the universes, and they let you play with it. So, for example, you can play with a team that has Illidan the Betrayer and, I don't know, Maderin the Dwarf and some swamp creature and whatnot. But the interesting characteristic of this game is you basically have two teams competing against one another. And one team has to pick 5 characters from the entire set, and so does the other team. Can I predict who wins based on the choice of characters? Because I'm assuming that there is some form of rock, paper, scissors element in this game. Reason being, in this game, there are different roles that you could play. So, for example, you have the healer, you have the assassin, you've got the buffy warrior, and you've got support characters and whatnot. So it might be the case that if you've got all healers, that your team's not going to be doing too well against all assassins. So can we devise some algorithm that is able to recognize this? And, gaming communities tend to be awesome. So if you go on Reddit, you're able to download a data set which has like 500,000 games in it, with lots of sort of things you could infer. So can we predict game outcomes? And there's a bit of a problem. So even though I have 500,000 games in my data set, let's just think about the search space. So if there are n heroes, my team can pick a combination of n times n minus 1 times n minus 2 times n minus 3 times n minus 4. That's the total search space of characters that this team could pick. Now, the opponent's team also has that search space, so I have to multiply everything together. So you quickly kind of come to a conclusion that the search space might be big, given a slightly bigger number of heroes. This is a big search space. In fact, even if I only have 6 heroes, I might only have one allocation in my data set if I only have 6, and in real life I have about 36. So the search space is insane. For every possible game that might have happened, I will not have a data point. That's simply the case. Especially because when I had the data set, it was like 5 months ago. And nowadays, they've even added more heroes to this game. So this task is becoming harder and harder. So, any random forest algorithm is going to give me the middle finger, because, this data set is too sparse. It cannot do anything with it. I think this is the next slide. Yeah, so I basically have 72 columns in this case, because I'm going for the 36 version of it. And out of these 72 columns, only 10 are filled in, and it will be just ones and zeros. So I have a prior that even a random forest or a deep neural net will have a bit of trouble with this, simply because of the sparsity. These models would work much better if I had much more data. So instead of trying hard to create features myself that might help the performance, let's use a bit of domain knowledge to help us out, and let's try to take the probabilistic approach, which might feel a bit Bayesian, if you will. 10 minutes, got it. So this is Team B, and Team B has 5 heroes. And the ordering here does not matter, but there's 5 heroes. Then here I've got Team A, and they also have 5 heroes. Also, the ordering doesn't matter. And I want to get from these heroes, from this team, to some sort of prediction. So I have to fill in a gap there with something sensible. How about I take this hero and that hero, and I combine them over there. I'm going to do something with them. But the idea is to just say, hey, let's look at all the combinations of all these heroes. And then for every combination, do something inferency over here. And then from all of these nodes, we can combine and do something inferency at P. So that will look like this. Which, it's not... Okay, so I could have drawn this better. Let's use a different type of notation. So this is what I'm trying to do, but let's use this notation instead. People tend to call this plate notation. But the idea would be I have a team A, I have a team B, and I'm taking all the combinations of heroes. I'm putting that in some form of plate, and for every combination, it's going to go to some predictor. Is this looking like a neural net? Nah. This is Bayesian, surely. So yeah, this approach might work. So what I can then do is, if I really want to go probabilistic, how about I know how often Team A won with this combination, how often this hero versus this hero. I know the ratio of wins. So how often did this hero win versus that hero? And that search space is actually quite a lot smaller. That's just n times n. So I will have data, quite a lot of data actually, for every single node here. All right? So what you would then do, you would be able to get all these beta distributions, and you can draw them for the entire team. And you can then combine them. This is a GIF. I'm going to let it run for a couple of times, so don't worry. I'm going to skip the slide real quick. But for every single node that you saw before, I'm generating a distribution of what I think will happen in the game outcome. That's my belief on which team might win. And given that all of these are beta distributions, you can just combine them all. So the thin lines are all the smaller nodes, and the thick black one would be the big node P, where I'm combining stuff. And here I'm doing it in sort of a probabilistic way. But to be honest, I can also just regard this, if I'm turning this into a probability of some sorts, like a ratio of who might win, then I can also see this as a tactic for feature generation. And then, okay, let's just put a neural network behind that. That might also just go ahead and work. And since we're on the topic, since we're thinking this way, I mean, this tactic sort of works. And I guess if you're looking at the x values and the outcome, because they will change up a bit, what you will notice is that it's not like I have hugely discriminative features at this moment. But then again, this is a highly optimized game for balance. There's like a team of very smart people who work for Blizzard who try to ensure that every single game that's played has players that are equally likely to, as a team to win. So if I'm able to find any type of, a game in balance, that already would be a huge profit, even if it's like only 5% or so. How about I go a step further? So before, this was the graph where I would look at like one guy from Team 1 and one guy from Team B. How about I take 2 guys from Team A and 2 guys from Team B? And surely per bucket here I would have less, but I would have a lot more nodes. And I can give that to P. So also this might feel a bit like a neural network or whatnot. But the idea is I'm doing feature engineering from something that makes sense probabilistically to reduce the complexity. And this turns out to be a computationally less intensive tactic. And if we're at it, okay, let's just make a deep Bayesian sort of convolution ensemble. You totally can. There's nothing that's stopping you. So we take the team 1 and team 2. We have all of these nodes that goes to some form of predictor. We have other nodes that goes to another form of predictor. And these 2 can go to another predictor node. It's kind of like a Bayesian way of doing a neural network, in a way, right? And being careful with, people might say that's not entirely true, which there would be correct, but this is a sound tactic, because I can actually still understand what is happening here. I can look at this graph and assign a form of interpretation to whatever is the outcome of these nodes. That's a nice property as well. Also, suppose I only know about 3 people from this team. I can still infer the rest. Also, something I like. Do that with your neural network. So this was, hopefully I've inspired you guys to sort of give this Bayesian school a chance, but it still confuses a whole lot of people, because professionals as well as students, as well as sort of professors at universities, they often suggest to me that this way of probabilistic thinking comes across as very new, if not super different. And the reason is, I'm never using, confidence intervals. I'm not using p-values whenever I'm doing a regression or something like that. I have probabilities, but I'm not really worried about p-values from tables or anything. I've so far never said anything about statistical significance, and I've not done an hypothesis test. So people always ask, like, hey, could you explain that? What's up with that? And you often get into this discussion of what the difference is between a Bayesian and a frequentist. So how about I just give my summary of that? All models are wrong, period. All models are super wrong. Some models, however, are useful, and you kind of have to wonder to yourself, where do I draw the line for what I tend to think is useful? Are you unsure about the data and you're trying to find the best single estimator to summarize this? That's a tactic. I guess I would call that frequentist. Are you unsure about the model, and do you accept the data to be the only truth that you have? And are you going to assign some uncertainty in your model? I guess I would call that Bayesian. Or are you willing to ignore all uncertainties when you have a black box that performs very well against a couple of test sets? These are the three schools. And the best example I could think of was a panda. When I came up with this example, I thought Wes McKinney was going to be here, so I figured talking about pandas might be nice. So let's say that I'm importing this image of a panda, and I want to have a model that describes what this panda is. Oh, camera. What I would then do is I would load this in, and I would check every single pixel value. A pixel value that has a low value, let's just call that black. A pixel value that has a high value, there's an upper limit to 1, let's call that gray. What I can then do, if I were, say, a frequentist, and I'm taking a very harsh example here, and some of the frequentists you can actually take serious, so please don't rant too much about them, but if I were a frequentist, my conclusion would be, hey, on average, a panda is gray. Which it is, which is completely fine. On average, a human being has one testicle and perhaps one breast. I still don't think that there are many people who, are like that. And what you then would do is you would say, okay, and if we want to figure out if something is a panda, how about we say this is the maximum likelihood estimation, and I know so that's the mean, and I know the variance, so I can do some confidence interval around this. And then, as a frequentist, in this silly example, you may come to the conclusion that a panda can be 1.5 white. So the odds, if you're doing, in my experience at least, the odds of something correct happening while doing frequentist statistics are good. It's just that the goods are a bit odd sometimes. If you're a Bayesian, I guess, so my definition of a Bayesian at least, you would say, well, my model has a bit of uncertainty in it. I don't have one maximum likelihood estimator for what a panda is. What I do think is that if I want to describe a panda, it seems sensible to say that they seem to be kind of white, not really gray, and very black. And to be honest, I think the fact that you can say it's really not gray, that's a characteristic of a panda, it's black and white, it's not gray, seems like a very sensible way of thinking about a panda. And I guess the machine learning community would be fine with saying something like this. So, dude, I have awesome test set performance. I don't know what a panda is, but if you give me a picture, I can definitely predict if it's a panda or not. Which, to be honest, but that's fine. I mean, that's a sensible way of thinking about it. And it just depends on where you personally feel that your risks are. In my experience, this is the triangle that's out there. And personally, yes, I'm on this side of the spectrum. I'm mostly interested in, say, doing Bayesian convolutional networks on time series that might be correlated. So exactly this intersection, that's where I'm going to be. But even I sometimes use tactics from here. So my conclusion is, please give this a bit of, some attention, because it's a very fine field. You might learn some stuff from it. But if I'm going to send you guys off with any lesson, just never let your school get in the way of your education. There's 3 schools out there. The truth is always somewhere in the middle. Thanks. And there's an appendix with extra probability stuff. Thanks.